All right, introduction to assembly language. I started doing assembly because I was procrastinating. I made a simple little to-do thing in Bash, and that didn't waste enough time, so I decided to write it in the most complicated language I knew of, which led me to assembly. Um, and I tried to get some help from the club, and it didn't seem like many people were very familiar with assembly, or at least not well. So I decided, you know what, let's teach it a little bit. Before I get into it, if you want to follow along, I'm gonna do a like uh, little demo of just a simple like hello world sort of thing. You're gonna need a 64-bit x86 Linux machine. It has to be Linux. I'll explain why later. And then I'm using NASM NetWide Assembler, which you can just get through your whatever package manager. You can use other ones, but the code is going to look different. And then you'll need LD, which is the GNU linker, which should be built into Linux, and then just any kind of text or code editor. About me, I'm a first-year CSEC major. I'm from Philadelphia, Pennsylvania. I own and love my car, um, which is covered by the big captions. 35. Yeah. I'm a gamer. I like to game, and I was a victim of the GPU shortage. I spent $1,000 on a 3070 Ti from Micro Center, might I add. And I'm a fiend for Tetris, and that high score is inaccurate. I got another 300K plus score 20 minutes ago. All right, so starting off, the first thing you're going to really need to understand for assembly is memory. You've got your different sizes of memory. Bit is going to be the lowest. It's just one binary, 0 or 1. That's like the absolute smallest there is. But in terms of actually working with memory, the smallest you can sort of move around is going to be a byte, which is 8 bits. It's got a range of 0 to 255 for decimal values. And then next we've got words. Words are a little less common. 16 bits, 2 bytes. Those are, if you've ever heard of first word latency, when talking about RAM, that's where that comes from. And then there's also V words, double words, which take a guess what that is. And then quad words, which is 64 bits, and in a 64-bit operating system, you're going to see quad words a lot. And how data exists in memory is you've got a number, and each number has an address. And in NASM specifically, to access memory at a certain address, you put square brackets around the number, so you see 0 is 0, but when you put square brackets around it, it's 70, which is what that binary up there for that data. And each address refers to a single byte of data. And then specifically in assembly, there's sections. Each sort of represents a part of the executable. When an executable is created, there's different parts. That's where all the data for it is stored, and then where all the actual machine code is stored. So data is the first section. I've got an example here where you have, it follows the format of, there's two different types of things you can put in data. You can either define bytes, where you or you can either define or equal. Defining is like each argument of a DB sets a single byte to a value. So for the example of ABC, 10, that will give us 4 bytes with the ASCII values of ABC, and then the binary value for 10. And 10 is important because that's the ASCII value for the new line character. So that way, if you print something, you have to add or you want to print something that has a new line, you have to add the 10 afterwards. So you see that a lot, specifically in Linux. And then equal creates a single byte with, or actually however many bytes is needed for a single value, which here it uses the $- thing, which will give you the $sign represents the current point in memory, and then message is the point in memory of the message, what message is, and so that will give you a value that represents the length of the message essentially. You'll also see that a lot because of how printing works. You need to pass the length of whatever you want to print. So you'll see that format to get the length. pretty easily. And then there's also BSS, which is uninitialized memory. You'll see this for buffers. It creates a certain amount of memory that has no value and just is used for storing however much data in the future. So you've got one named buffer, which is res-b, b stands for bytes, and so you'll see there's 5 bytes in memory highlighted red, which is the color I've chosen for buffer. And then I've got another one for descriptor, which is a quad word, res-q. So you can see there's 8 bytes for the quad word. And then text is the section where all of your logic is. That's your code, essentially. And you can see sort of what this would look like in memory. You've got the purple section, which represents your message, and what the message will sort of variable will actually look like when you execute the code. It's just the value for the first memory address of that area. So you can see it's 1, and that first section is memory address 1. And then buffer is also going to be the memory address of the first part of that area of data. And you can see that's 5. It's the first address after the 4 bytes that message represents. And then message length is just a straight up value. It doesn't represent a memory address. So that's 4, but it doesn't represent the 4 memory address. And then the descriptor is 10 because it starts at the 10 memory address. And then registers. Registers are what you are going to be the main sort of, they're little pockets of data that are connected directly to the CPU. Very important for a lot of things. They are used for system calls, which we get into soon. There's a lot of different registers. The main 4 are RAX through RDX. That's B, C in the middle, which represent accumulator, base, counter, and data. These can kind of be used however you want, but they each have sort of specific uses or use cases that were set forth when the standard was created, and they've been extended. Initially, it was just 16-bit, I believe, and now you see after AX, it became EAX for extended, and then RAX. I don't know what the R stands for, but it's the 64-bit version. And this has several different ways of representing it that refer to different amounts of data. So RAX is all 64 bits. You can see at the very bottom, you have the red section that's all 64 bytes is represented by RNX. And then EX represents the first 32 bits. And then just whatever X is the last 16 bits. And then you have the highest 8 bits of that 16 bits and the lowest 8 bits of that 16 bits, which are represented by H and L respectively. And beyond the RAX or RAX through RDX, you don't have that 8-bit high version, which is kind of annoying. But the other ones are RSI, which is the source string operations, hence the S, and D is the destination. Then you also have the stack pointer and the base pointer. These you aren't going to mess around with that much or as much. They, as well as the instruction pointer, they're kind of used in other or as part of other instructions that are going to be doing with the stack. And RBP, the base pointer, points to the bottom of the stack essentially. The instruction pointer is where you're going to be getting your, or is where the CPU is going to be getting the next instructions from. So if you mess with it, you have to be very careful, because if you want to skip an instruction, it's not advisable to just add some amount to the instruction pointer, because you could end up going too far or too short, and that could cause some havoc. And then you also have R8 through R15, which are just for pretty much anything, just storing a value somewhere where you want to have easy access to it, fast access to it, because these are going to be by far the fastest to access from the CPU, because they're just right there. They're as close as you can possibly get. And then in execution, you have your executable. Oh, it's cut off. I forgot about that. Generally, on top of the actual file of your executable is going to be, or the first part is going to be your data. This is where all of the, if you have hello world defined initially, it's going to have that ASCII value in that upper data part. And then you have the code part that will be actually what is executed. And 64-bit CPUs draw on 64 bits at a time. Shocker. And then the way it works is there's opcodes, and then arguments for that opcode, and the CPU will know, quote unquote, how many arguments it should take for each opcode. So for this example, you have a 1 byte opcode that has 2 arguments, and 1 byte, as I said, is the lowest amount of memory that you can handle, like directly. So for the first operation, it's going to know that the next operation that you go to is 3 away, or is 3 bytes away, so it's going to add 3 to the instruction pointer. And then not all opcodes are 1 byte, but in this case, when we have 3 opcodes with 2 args that are all 1 byte, that doesn't fit into 64 bits. So once it gets to that final opcode in the 6th memory address, it's going to have to pull another 64 bits from memory in order to get that, in order to have that operator work. So it's not going to draw like the next 64 bits. It's going to draw 64 bits starting at that 6 memory address. And then system calls, this is how you really interact with anything on the system, because other than this, you can pretty much just do, or without system calls, all you can really do is math, which is boring. So for an example, or the call numbers are put in RIX, and then you have all of your arguments in various different other registers. So RDI is the destination one for most things that have to do with strings, but for anything else that doesn't have to do with strings, it's just a generic first argument, and then RSI is next, and then RDX, and then it's R10, and then R8 for some reason. I don't know why that's not, it's not 10, 9, 8, I don't know. But for printing, you've got, is the same as writing. You're writing to the standard out, if you ever heard that. So you need to put 1, which is the system or the call number for writing in RAX, and then RDI, that's going to be your destination. 1 is the descriptor for standard out, so you're going to put that in RDI, and then you're going to put the pointer, or the essentially memory address of the first byte that you want to start printing in RSI, since that's your source. And then RDX is going to be the length. And so for hello world exclamation mark, that's 12 total bytes. So you pass it 12, and that way it knows when to stop. And then you use the syscall opcode or operation to let the system do its thing. And that's effectively the assembly version of just a simple print. So common instructions outside of move, which is just moves from one location to another, are add, subtract, multiply, divide. And then you also have compare, which is going to be how you do any kind of conditional stuff in assembly. You have to compare 2 different things, and you can, there's a whole bunch of different jump instructions. You've got JE is equal, so that means you can go to a different part of your code if the values are equal, and then JL jumps to whatever part if it's less, and then JMP is unconditional, which will just jump regardless. So if you want to immediately like get to a different part as part of another, for example, if you're, I don't know, I can't think of an example, but instructions and opcodes are pretty different. You can see there's a lot of different actual numerical opcodes for a single move instruction. Each one of them has tiny little differences that matter to the system but don't really matter to you, and this is kind of what what the assembler takes care of. You mostly write the higher level stuff, and this is the lowest level you can do. And that's a lot, but that's also just the ones that are just called MOV. There's also these, which are more different moves. Then there's these, and then there's a few more. So there's a lot of different values, and your assembler takes care of all that for you. So thank you, assembler. So my setup, I just have a pretty simple, well, I have a setup that I've refined over time. I've just got a browser to the right. You won't actually see this since my laptop wasn't working, but I've just got a browser to the right, which has anything that I need. I normally keep a reference table that has each of the syscall numbers and then each of the arguments that it needs, with sort of a description of what each argument is for and sort of what you need to pass into into each register in order to get that to work. And then I have a register reference table, which is just, if I can't remember, oh, what's the, can you access the higher 8 bits of the last 16 bits of R7 or something? That helps a lot. And then I also have the NASM docs, just because there's a lot of little things that NASM does that are really useful, and it's useful to have somewhere you can check how that works. And then you have the ASCII table. Since all of what you're doing is numbers in assembly, it's really important if you're doing anything with strings to be able to like check what the actual values are. So if you're like trying to make sure that something that you're passing the right value in, and you want to like look at the actual string, it's not going to show up in GDB, which is a debugger, as a string. It's just going to show up as a number. So you need to be, so it helps to be able to easily cross-reference that with the ASCII table to make sure that that's the right things. Speaking of GDB, I have a Tmux setup, which is just my code editor as sort of the central thing. And then to the right, I just have a normal terminal that I use for debugging. And below it, I have two sections. One is a file in the actual Linux kernel that shows all of the error numbers as numbers, and then it has a comment that explains sort of on a very basic level what each number does. You can also go through a whole bunch of other files that also explain some other sort of things. There's one fcntl.h, which is all of the file control stuff. So if you want to make a file and make sure it has this certain permissions, it kind of has the values that are the what the permissions, what you need to use in order to get that, or what you need to pass it in order to get those permissions set for that file. Then I have another file, which at this point is kind of redundant, with the syscall reference table that just shows the specific numbers. That is also another file that's actually part of the Linux kernel. And in debugging, I use GDB. It's mostly, or it's often used for C, but it's also very useful for assembly. You pretty simply just run GDB on the whatever executable, and it'll load your program, and it'll start running it whenever you're ready. You want to run the layout ASM reg command in order to get it as to look good, essentially. And then you use the B or breakpoint command, or break command, to create a breakpoint somewhere, and you can use the name of a function, or like functions are just sort of symbolic things that you can jump to that are part of NASM, and just runs the program and stops on whatever breakpoint. And then S goes, once you're at a breakpoint, you hit S and it continues to the next instruction. And then C just continues running until the next instruction once you hit a breakpoint. And whenever a syscall fails, in order to figure out why it failed, it puts the error number, or negative version of the error number, in the RIX register. You can see that's the file I was mentioning before, with each of the different numbers and a little comment describing what the number represents. But also in the documentation, the Linux documentation for each specific syscall, you can, there's like specific things for each different syscall that explains how this specific number pertains to that specific syscall, beyond the very generic, vague descriptions that are in the kernel. So for the Hello World example, I'm going to be doing slightly different. I'm just going to be having a file with Hello World written in it. So we're just going to have to open the file, read the file in, then write from that buffer that we've read the file into the standard out, close the file, and then exit. So pretty short and pretty simple. And that's really. So yes, you can see the setup. It's a little different than on my. You can see there's no. I don't know how to zoom in on this. Okay. So to start off, we're going to need to make the actual. Control shift. First off, we're just going to need to make an actual .asm file in order to have a place to write the code. So starting off, I always like to define the sections I mentioned before. And a little note for Vim specifically, if you're also using Vim, it won't automatically detect that it's NASM, so you have to set the file type to NASM. Just to get the syntax highlighting to work properly. And then after data, I like to do the BSS. And then text for the actual code. A lot of the time, people put the data and BSS at the bottom. I don't know. That's just not what I do. And then also another slight difference between, or pretty large difference between assembly and a lot of other languages. You have to actually call the exit syscall at the end, otherwise it'll keep executing beyond your code, and that'll throw a segmentation fault. So I always like to just put that on at the very beginning. It's a pretty simple instruction. You have to move 60 into RIX, which is the syscall number for exit, and then into RDI, you need to put the whatever your exit code would be, which will be 0 as the sort of standard exit to say there's no problems. And then I also like to use, or to have something that I can jump to there. So I put the exit sort of label just so I can at any point jump to that point. And then you also need the underscore start. This tells the assembler where you want the code to, or the executable to have its first start point, where to start the execution. And then you have to start off by, since we're going to be reading it from a file, we need a buffer. So in this, I've just defined a buffer with 128 bytes. That's what the res B, the B stands for bytes. And so that gives us 128 bytes to work with, which is way more than we need since we're just going to be doing hello world, but it doesn't hurt. And then you're also going to need another value that's going to be the file name that you're going to pass to the system in order for it to figure out what to do or what to read from. So you just give it a name and then add a colon at the end. And then db as defined bytes, and you use db for strings just because of each byte, or in ASCII, each byte represents a character. And I'll just call it hello world.text. And it's important with file names to add a null byte to the end, because unlike with printing strings where you pass it the length, you don't do that for opening files. It just goes until there's null byte. So you always have to make sure that's there. Sometimes you can, if you don't use it, it might work initially, especially with the buffer. It'll just read, and then once it gets to the first byte of the buffer, that'll be null. And so it won't cause an issue, but then if you add any more stuff to your code, then it can cause some major pain. Then I'm also going to have a buffer length just to pass to the print function. So we're just going to print the entire buffer, which is just going to be the the hello world that's going to be in that text file. And we use EQU to say that we just want 1 byte with this value, or however many bytes it needs to represent that value. And then that way we can get to the actual doing of that. Oh, one more thing, I forgot about this. We also need to store the file descriptor. This is just a little tiny integer that the system will give us in order that we can use to reference the file without having to pass the entire file name. I like to reserve a quad word for this just because that's the size of the register, so you can just move the entire register into that without having to mess around with anything or worry about any kind of overflow or anything like that. All right, and then we can actually start by just opening the file. And to leave comments in assembly, you just use a semicolon, and then anything after that will be a comment. This is really important because of how abstract assembly code is. You're pretty much going to need to comment most lines, if not all of them. Maybe not for some very sort of clear system calls that are obvious to anyone that's familiar with assembly, it's or even simple stuff like adding. But a lot of the times, even simple arithmetic, it's going to be kind of confusing because you aren't sure where the what the purpose is of that arithmetic. I'll show you an example of that in a second or later. So we're going to start off opening the file. So the file open syscall number, you can see down at the bottom, is 2. And then we have to move the destination is going to, or RDI, the destination register is going to have our file name. This is going to tell the system what file we want to open, obviously. And then we need to use RSI to tell it what permissions we want to open it with, whether we want it to create a new file if this file doesn't exist, whether we want to just read from it, or we want to read and write, or just write. We just want to read, so that's what 0 represents. And then we do our syscall. And then after that, we're going to get a file descriptor in RAX. So we want to store that so we can work with it later. And here we have to use the square brackets so that it'll write it to the buffer that file descriptor is, or the null bytes that file descriptor has kind of created and the file descriptor references. And then we can read from the file. So for this one, you can see that's 0 for our syscall number. And other than moving 0 into RX, you can also XOR RX by itself, which will also result in 0. You see that a lot. I believe it's somewhat faster, but doesn't really matter for something this tiny. And then RDI is going to be the descriptor of the file. And then RSI is going to be where we want to write the file to. And we're passing the value at the file descriptor to RDI rather than the file descriptor because we don't want to, because it just wants the actual descriptor, which is just a small number. It'll probably be 3 when we look at it in GDB. But then for the buffer, it wants a pointer to some area that it can write to, so that's why we just give it the buffer without the square brackets. And then in RDX, we have to pass how much we want to read from the file, just as a value. And since that's our length of our buffer, we just pass it 128. And when reading a file or reading anything, it will continue either until it reaches the end of the file or it reaches the length of your buffer, so that way you don't need to worry about having a buffer larger than the file and then reading outside of that and causing issues. But that ends in REX, it'll return how many bytes that it read, so that way you can, if you're trying to read a really large file and you only have a buffer of a certain size, that way you can check that if the buffer length is the exact same as how much was read, you know there's probably more in the file, and you can go back and read it again to keep getting more information. And then we want to close the file since we don't need it anymore. Closing is 3. So pretty much the same thing. This is a lot of assembly, just kind of remembering this kind of stuff. It doesn't seem very interesting, but where it gets really interesting is doing more complicated stuff that isn't really super intuitive to do. And then we don't need anything else, just needs to know what file to close. And then you can just syscall. And now it's as simple as just printing out. You already saw the print that I did before. It's just RX1. Already got where we want to print, send it out as 1. And then what we want to print in RSI, the source, which is our buffer, and how much we want to print in RDX, which is going to be our buffer length. And then it's just a syscall, and we're all done. Since we already wrote the exit at the very beginning, we don't need to worry about that. But if we were writing a larger program and we wanted to just execute this code and then exit, we need to have it jump to the exit, which we obviously don't here because it's just right after. It'll come automatically. All right, and that's how we can write it, simple as that, but we also need to assemble it. So assembling and linking, this is the command that I use pretty much just entirely. I don't think there's any other than specific, like very specific things. This is kind of a catch-all. So NASM is the assembler that I'm using, and we start off by giving it the F option and having ELF64. ELF64 is the executable format that is used by a lot of different, pretty much like most Linux-based things, Android, and 64 is just 64-bit. It stands for the executable and linkable format, and it's just standard. And then G enables debugging, so for using GDB, we need to have that toggled on, and then we use the capital F flag to say we want to use a specific debug format. That's going to be little bits of code or little bits of info that it sort of injects into the assembled code in order for the debugger to know what's kind of going on. And I'm using Dwarf. That's another fairly standard thing. It doesn't stand for anything. It's just fantasy like ELF. And then you just pass the file name and then use the O flag to tell it what to output. And we're just going to use whatever our original file name is with the .o as the output. And then we use LD, which is the GNU linker, to link the file name, which is used normally for connecting multiple different files of multiple different object files together, so that way you can call functions from between different files that, like, for example, if you've already wrote something that does a lot of stuff with reading large files or something, you don't have to completely rewrite that code. You can just link them together and then use some of your old code. And then you just use the .o to say what you want the file name is for the output. And then you just use / and whatever the name of the executable is to run it. I like to put this in a bash script as well, just to make it a little easier to do. Plus that way, if there's anything you need to do, like for example, if we were writing to the file, it might be important to make sure that that file is the same at the beginning, so that way you don't write some random stuff to it and then you get some result you don't expect when you try and read it again after having written something. So you can sort of reset it to what you want. So I'll just do this quickly. You also might notice that I'm using printf instead of echo to get that hello world in. That's just because I want the new line at the end, since we're not printing our own new line. If we didn't do that, then when we ran the code, it just would all be on the same line and it would look kind of ugly. Then I have to make that script executable and then just run the script. And then if there's any errors, yep, you can see I misspelled something and did something wrong with that. Oh, that's what I did. I forgot to do that in Bash. And you can see, okay, the buffer length is not defined in Hello World, our assembly project. That means that I probably spelled something wrong. And you can see there, I called it bufflan instead of buffer length. That's a very common thing. I've done that a lot. Especially with these very long files, since it takes a super long time or just a lot of lines to do very simple things, it's really easy to just kind of lose the names of your things. I sometimes would keep another one open just so I could reference back to it. And now LD couldn't find underscore start. Oh yeah, I forgot to do the global underscore start. That defines it as a global variable rather than just sort of a label. Yeah, I'm not doing well right here. And also printf isn't working. I'm not going to worry about that and just brought on. And it should be as simple as like that. And it doesn't work. Okay. Okay. Well, rather than spend a bunch of time debugging that, how about we get to some stuff that I actually have prepared. So this is the actual kind of stuff that I've actually worked on that I'm not doing in front of a bunch of people with one hand. So I've made a few sort of random projects over the time. Dec to bin is just a decimal to binary converter that I wrote pretty quickly because I was procrastinating a an SSA assignment where I had to convert IPs from decimal to binary, and that made it slightly easier, even though it took way longer than just raw dogging. And then file test was just a early thing, and then that I was using to test reading and writing from files. Hangman, I'm pretty proud of. This actually does work. I just tested it. Kind of does what it says on the tin. It takes a random word. It tells me the answer right now just because I wanted to make sure that it worked. But it gives you the guesses. You can enter your guess. It'll fill it in if it's right. And then if you get a word wrong, it says no match, and it'll read back from your guesses. If you just do the same thing over and over again and lose, it'll tell you you lost. Yeah, I'm pretty proud of that. It is pretty simple, but it's also not, because it's obviously it's assembly, and something as simple as that is well over 100 lines of code. I didn't comment this one very well, but if you want to see one that's fairly well commented, actually very well commented, if I can keep my own. my to-do project is pretty simple in concept. It just gives you a list of things when you run it like that, or you can pass it something to add to the list. And it'll give you that. It has line numbers. You can remove stuff. For example, if I want to remove line 1, simple as that, and it's gone. This one is a culmination of about a few months of work. It is, as I mentioned, 400 lines of code and fairly well commented. One of the most difficult things, one thing that very much surprised me in terms of its difficulty, was just doing the line numbers. And it doesn't work past, I think, 100, just because essentially what I was doing, or because each byte is its own value, and for the line numbers, I'd have to, every time it went up 10, I'd have to have another sort of case or to move the bytes over and like reset them all to the correct value. So I didn't feel like doing that a bunch, or like doing recursion or whatever that would do it more better. So I just sort of capped it at 100, because I figured if you have 100 things on your to-do list, you probably have bigger problems than line numbers. Yeah, is there anything anyone wants to see in this? Or any questions about assembly? I probably don't seem that knowledgeable, but I've spent a lot of time on this, and I know a couple things. Oh yeah, that's actually one more thing, is the, hold on, arguments. Arguments in assembly are a bit different than other things. They are the first things that appear on the stack whenever you pass in, or whenever you run the executable. So you see I pop Rx, that gives us our argc, that's the total count of arguments that have been passed through the, whatever it is, to the program. And then the next thing on the stack, which you get from pop as well, is going to be the pointer to all of your arguments, which is just kind of all together in memory, separated by null characters. So you can see to get to the next argument, and the first argument I should mention is just the how the program was called. So if you do / something, that your first argument will be / whatever the name is, and then it will be anything you put after that. So you have to make sure you get through that before you try and like get any actual arguments. That messed me up a lot very early on. And then you just kind of have to just move through, check if it's a hyphen in this case, if you want to use flags. Or if it's not a hyphen, then that means that I want to add it to the list. It must be something that's must be another thing to add to the to-do list, so it jumps to that point. If it's a hyphen D, that means I have to remove something, so I have to jump to that point. And if it's hyphen anything else, then it's an issue, and I have to print out an error. And that's vaguely how it works. You can see, if I go to the very end, this is 411 lines of code. With, I think, probably no lines of white space in between each instruction, and a lot of comments. I think we just went past. Yep, this is the line number printing stuff. It's more common than code. It's, or is it actually? I don't know. Here we go. This is the line number stuff. It's a lot of stuff. It's essentially every time that the program runs into a new line character in the thing, it has to iterate a counter, check if that counter has gone over 9. And if it has, then it has to add that value to the next byte. And then if I wanted to keep it going past the 100, I'd have to check that byte then, and then add up there. Definitely possible, but not worth it in my opinion for this. And it does a lot of byte-wise stuff, like moving things around certain amounts, and it was probably the most difficult part of this entire thing. And then if you want to see how long or how difficult this would be to do in any other language, I actually did that in several languages. And I actually have this on GitHub, and if you look on the GitHub, it says that the code breakdown, I believe it's 60% assembly. So that means that just the one assembly version is still more than all of the code in every other language I've done combined. So I'm pretty proud of it. It's not very useful, but it took a long time, and it was honestly very fun. I think assembly, it isn't like a very useful language in a lot of cases, except in really specific stuff, but it's really interesting to just kind of throw yourself at problems and having to think of them in really different ways that's just completely different from what you would normally expect to do. And I had a lot of fun doing it. Yeah, that's it. Yeah. Thanks for watching. Any questions?